Okay, welcome back everyone. Hope everyone had a good winter break. Hope second semester is going well so far. This is the beginning of machine learning fundamentals, phase two. From a raise of hands, who has come to a phase one um workshop? A little higher, please. Okay, so around half of you. For those who weren't here, right? Which one of you guys have done an ML project in the past? Yeah, I know you have. You made a library. Okay, that's fine because this is the exact place to go to. Um, so yeah, let's get started. So content for today, we're gonna start with a very, very fast-paced one recap. I'm just gonna talk about what models we went through. I'm not gonna go through them in detail. You can refer to those slides or you can research those yourself because phase two is more about the planning of the project, how a typical machine learning project workflow is like, right? Yes, you can have a lot of machine learning knowledge, but how can you actually put that into application to make a project for a resume? That is what we're going to be mainly going through in these couple of workshops. Second one is the phase two plan and what should you work on, blah, blah, blah. So phase one recap. For those who weren't here, these were the models that we have gone through. Some of them may sound pretty familiar to you, right? So yeah, linear regression. I'm sure that many of you have heard of it before. I know how it works, right? Logistic regression, neural networks, decision trees, Bayesian models, deep learning methods, and evaluation and practices. So once again, if you want any reference to how these models work, just go on the UTMIST site and there is an MLF phase one tab for it. Is everyone good so far? Anyone have any questions? Also, may I ask, who here is from U of T Hacks? Okay, I thought there were people from U of T Hacks going here. Okay, so that's yeah.
Oh, yeah, just one more thing to say. So we voted some of the most useful models on the slides. So yeah, those are the models you're probably gonna deal with. Um, yeah, so for linear regression logistics, you probably won't use it, or at least simply. So you can just focus on the voted model mainly for your project. And so yeah, here's something you're gonna do for phase two. So it's a lot more self-directed. So it's not going to be like we're telling you like phase one, oh, let's learn this thing on week one, and then what to learn next, what after. And instead, you should be the one taking the initiatives to think about what you want to learn or what you want to do, right? So a few things you'll probably do is first of all, think about your projects, like you have an idea, whatever, and that means you can't like really do projects on everything because you have to be more very specific in one direction, and then that means you'll probably need more knowledge in that specific direction as well, which involves lots of self-learning, as I said, reading papers or of course coding and asking advice for help. Yeah, and yeah, this is like basically what ML in real life is, right? When you're working on research or whatever, um, you will do lots of like paper reading and coding and then like iterations of like trying different things and then doesn't work and then try again, something like that. So hopefully this phase provides you some I don't like let you get a sense of what it feels like to do ML in real life. Yeah. Did you make this?
Okay. So if you're wondering what you're gonna get out of today, these are the important points we're gonna go through. First of all, how can I ideate? I think I pronounced that right, or brainstorm an ML project, right? What data do I need? How can I actually analyze the data sets that we have? Because in real life, data is often very dirty, very noisy. I'm sure we all know. And I'll talk a little bit about data processing as well as selecting the model. So once again, for those who are here in phase one, this is not going to be as technical as phase one, right? We're not going to teach you like the math of like the neural networks or something. Rather, we're trying to get you to think and organize the ML project that you're going to be building in the near future. So does that sound good? I got thumbs up. Thank you. Go for it.
Okay, so we're gonna go through the planning for phase two for a while. So basically today is some recap, logistics, and then we'll introduce some how to get started with your project, and then also forming group a little. We'll also do some project demo, which are project done by Hayden. He's not here yet, but he will hopefully come soon. And then that's for today. And then for the second week, which is next week, we'll do a proposal workshop. So the purpose of that is basically you need to formulate your projects, right? So you need to have the correct scope or difficulties. And the purpose of that or proposal is to let you draw your idea into some concrete methodology or implementation, like how you can do this project. And then you have like a detailed steps and all of that. And then you'll submit a proposal to us. Between like second week or third week is due like 31st. So what's the purpose of that is we're going to look at your proposal and then we're going to say like kind of give you a direction of like, is it good or maybe it's too difficult or too easy, right? Is like doable in this semester or probably like take 10 years to work out. So we'll kind of like give you some feedbacks on it and then maybe something you can change to make it like easier or do your project better. So yeah, mainly it's just for your understanding and then the feedback. Yeah. And then after week three, it'll be just work period. And then we'll have mentors here to like help you to help you like if you need help or otherwise you can just like be here with your group and then be like a dedicated time for you guys to work together.
Yeah, and let's also ask questions on the Discord channels, and we'll announce more on that later.
Yeah. Also for those who are planning to attend the rest of sessions online, it's a little bit difficult for the work period and office hour. Well, I think we'll provide Zoom like online help, but we'll prioritize those who came in person here. So yeah, but and then it's also I think it's easier for you to come in person and then work with your team in person. So but we'll try our best to help those people who are not able to came. Yeah. Okay. So the first thing you probably ask for this thing is like, what should I work on, right? So there's millions things you could work on with ML, and then you probably say, oh, like how do I narrow my direction or know what I want? So the first thing I'd say is that you should think about your interest, right? Something you like, or some problems you have in your real life, and that you think machine learning could provide a better approach to deal with those problems or interests. So that's really like personal specific, I'll say. So I can't really give like a specific example, but as an reference though, we took some sample projects given by the course APS 360. Hopefully you have access to the slide so you can see it, but we're gonna, yeah. So basically this is the document. There are like a bunch of projects and then they're all deep learning oriented. So it's probably going to be a little bit different. I mean, it's just neural network based, which you learn in phase one, but lots of them involves more advanced architecture or, so you probably have to do some extra learning if you do want to do one of these projects. But I'll say, like lots of, lots of these projects are like very typical projects. So probably see like those projects already done by like a million people. So I still suggest you to think about something you want to work on and then have a little bit of like personalization in it. Although if you don't really don't have any idea, you can work on one of these. It's still a very good practice for your learning and ability. So yeah, I can just like take a look of what these things are, like music genre classification, traffic sign recognition, face detection with a mask, Pokemon generation, so something like that. Wait, say classification? Yeah, classification. So there are a bunch, but it's okay. Yeah, so there are a bunch. You can take a look right now or like a little bit later. But hopefully this gives you like a starting point that you can brainstorm your idea based on these projects or like yeah, just to see what things would look like. I think I shared it, so it should be okay. Yeah, but like everything in the document is like very common. So if you want something more nuanced or specialized, you can definitely brainstorm your own idea. That's it. And have some alternative projects you could work on. Projects is first you can do some paper reading and re-implementation, which is very typical in research, right? So I'll say doing this requires lots of paper reading and paper reading skill, and it's probably a bit math heavy because you all go through like lots of formulas and whatever. Um, yeah, but I think it's very good if you want to do a research kind of based project. So what we'll do is like you can try to recreate what the paper's been doing, try to implement their code, like right, and then see if the results matches their results. Um, and you can also like after you maybe re-implement the entire pipeline, you can see maybe you can make some modification to it, right, or run it on different data set and see the result. So it's more research oriented for that. And second was like API based projects. So you can do, I mean, API based projects mainly ML, LLM applications. So basically what you do is you use like GPT or Gemini or whatever, right? You use their API and then you get a response. You can do something like that. It's like lots of things involved like chatbot or whatever in this direction. And in terms of token, so I think Google Cloud will provide you some free credits if you're a new user to register in their account. So yeah, that should be sufficient for the project, to be honest. But if you need extra token, you'll probably have to buy on your own. But it's not really expensive. So unless you're like running very large scale projects, it should be like doable. Yeah. And third one is implement your own library. I think Abdul, right? Like, yeah. So basically, Abdul did something like this. He tried to implement his own ML library, so called, which is like a simpler version of like PyTorch, basically, and then it will actually help you to understand what's going on under the hood of those libraries. And I think it's a very good like learning opportunity as well. So, any questions so far?
Okay, so I'm gonna start with the simple ML project workflow. So generally, for a beginner ML project, we can split this into around 6 to 7 steps. The ones highlighted in green are the ones that I'm gonna go over. Yes, I saw what you did with your hands there. Um, anyway, um, usually start with the problem definition, and then data collection, and data exploration, data pre-processing, and choosing models. And the most important thing to keep in mind right now is that machine learning is a process. It's all about learning the steps you go through. So the first thing is the problem definition, right? Just like when you are solving a real life problem, don't think about the coding, don't think about the model, don't think about optimizing yet. You have to think about the following, right? It all comes down to simple things. What is the input of your problem? What is the output of your problem? What's the type of ML problem? So, does anyone remember the different types of ML problems? Yes. Yep. Any more? That's okay. That's what I'm going to talk about next. So every ML problem, they can be framed as features and targets, which is just fancier ways of saying input to output. And the types of ML problems, for beginners, usually there is regression. Regression is where you would generate like a numerical value. For example, we've all heard of linear regression, right? Let's say you want to make a model to predict how well someone's going to do on a test, right? It's going to output some number indicating your mark. That is regression. Any questions about regression? Okay, next there is classification. So the name of this should tell you the whole story. For example, let's say you have a picture, right? And you want to classify whether it's a cat or a dog, right? That is classification, right? You don't output some number like 8 or 9. You're trying to output whether or not it's a cat or a dog. And last thing is clustering. Clustering is pretty difficult and it requires you to know something called unsupervised learning. So if you're interested in that, you can kind of look at yourself. We're not going to go through that because we don't have enough time. So does anyone have any questions so far? No? Okay, so some examples here. For example, let's say you want to predict house prices, right? Your inputs or your features can be many different things, right? For example, the size, the location, the age. The output would be the price, right? So that would be a regression problem. Or for example, a cat species recognition, right? You take an image, the output would be the cat breed, and that's the classification problem, right? So for example, I kind of just gave it away with the name, but if you want to make a model about spam emails, right? What do you think could be possible inputs for a project like this? Let's say I want to classify spam emails. Yes. Yeah, that would be the output actually. Because the output is like what you classify. Yeah, the text itself, right? And maybe you will include other information with the text, right? Maybe the date it was sent, maybe the day it was received, or maybe the day that someone replied to it, right? These are possible different inputs that you can put into your model in order for you to try to say, hey, oh, whether or not this is spam or not a spam email. And of course, given a name, this is like a classification kind of problem. Does that make sense? Does it make sense that you will have like a bunch of different inputs in order to be able to kind of make like a distinction of whether it's spam or not spam? Okay, so yeah, you can formally make teams now and actually brainstorm some ideas. Yeah, so yeah, make some teams, talk to your friends or someone near you. I'll give you guys around like 5 to 10 minutes ish. You guys can brainstorm some project ideas. Okay, so I hope you had a pretty good taste of brainstorming a machine learning project. For those of you in like engineering, this is like exactly like brainstorming for an ESP project. Um, if you're an engineer, you'll know. If you're not, I'm sorry. But okay, so after deciding on the input and output of your project, of course, you will need some information to do training with, right? Lots of time is spent on data collection and understanding before you even think about what model to use. So some of the most common forms of data are databases, public data sets, APIs, sensors and devices. And yeah, for each of these examples, can we think of, I guess, examples of each form of data? Like, for example, databases, right? Can someone give me an example of a database we would find data in? Or maybe a public data set. Can anyone give me an example? Yes, Abdul. Yes, Kaggle. We'll talk about that later. Yeah, MNIST data set. Those are very common data sets used for especially more beginner friendly machine learning projects. How about for public data sets? Or how about for sensors and devices? Can anyone think of any ideas? Now keep in yeah, is what? How do you spell that? Yes. Yes, so our friends like Gapminder, that's also an example. So here are some more examples, right? So databases, right? Let's say you work at a company. You will have things like transaction records, user accounts, logs, right? For public data sets, the most public of public would be like a government data set, right? The government has like public health data located, public health data, right? Sensors and devices, right? So who here has like built a robot before or like worked with robots before? It's fine if you don't, but many robots may take like pictures, or for example, your computer. You might have mic audios. These are all kinds of data that you can use for your projects. So, anyone have any questions? So I'm good to move on, right? Okay, so where can I find these data sets? This is probably the question that you guys are going to be asking. So, first of all, our friend said Kaggle. Kaggle is a very large platform for data sets and competitions. It's usually very, very clean, which I think is a good thing about Kaggle. You don't have to do well, you still have to do pre-processing, but for like a beginner ML project, it's really good. Next is Google Dataset Search. So some people might not know, but Google actually provides their own search engine for databases. Next one is government open data portals, right? Like I said before, or health, or even traffic, or censuses, right? Some more different data sets that you can use or databases you can use. You can try these, but be more careful with them. So first one is called Hugging Face. Who has heard of Hugging Face here? Yeah, so what is Hugging Face? Can someone explain to me? Yeah. So it's an open source platform for ML models, like it says there. It provides you open source models, but also provides many data sets. If you're doing more advanced machine learning, especially regarding natural language processing or LLMs, Hugging Face data sets are the best, some of the best data sets you can find. You can also find GitHub repositories. I'm sure we all know what GitHub is. Um, and also UCI machine learning repository. This is often used more in academic data set collection. Anyone have any questions? Okay, so let's say you find your data set, right? What are you gonna do? Well, of course, you have to inspect your data, right? Like you have to first look at how many data points you have, right? For example, let's say I have a government data set of for example, the health for about healthcare, right? You should look at how many pieces of data is in there, right? Of course, logically speaking, the more data, the better, right? The less data, the less you can train it on, right? We can all agree on that. And for each data point, you should look at what features each data has, right? For example, let's say you have a housing price data set, right? How many features are there, right? What are we looking at in order to be able to predict the housing price, right? Is it the size? Is it the age? Is it the conditions? And the ultimate goal is that you should be able to explain your data set very simply. Does that make sense? Yep. So ask yourself, does it make sense, right? How many data points and examples? And are the features numerical or categorical, right? So if you really want to look at an example of a data set, I'm going to do that right now. I'm going to have to change my screen sharing, I think. Hold on. Yeah, so everyone can see this, right? So typically, if you go to a Kaggle data set, this is what it's going to look like. I hope I can zoom it out a little bit more. Um, so yeah, for example, if you want to predict like the price, right? Here's the housing price. And then here are all of like the different features that you would need. Does this make sense? Okay. Right. So if you want to, I guess, inspect this data set, you just tell yourself, oh, if you want to really explain this data set simply, you just be like, oh, this housing price data set has the price and has the features of the area, bedrooms, bathrooms, stories, blah, blah, blah. Does everyone understand this? Because it's very common for you to be very confused with the numbers, right? In machine learning, it often becomes like a jargon of numbers, and oftentimes it becomes not very interpretable. So it's very important that you understand what is happening in your data set. So last thing, do a sanity check, right? Oftentimes your data set can be very, very dirty and noisy, right? There could be empty or missing values. Or are there any values that are impossible and unrealistic? Or is there something called class imbalance, right? For example, let's say I want to make a cat and dog classifier, right? Let's say I have a bunch of pictures. I want to classify if it's a cat or a dog. If there's 500 dog pictures and only 100 cat pictures, that's a class imbalance, right? Ideally, you want to find a data set that has a balanced set of categories. And these issues can be handled with data preprocessing, which we will get into very soon. So, any questions? If none, I'll keep moving on. So, data preprocessing, like I said before, raw data is not ready for machine learning, right? They can be very messy, inconsistent, and incomplete. So, can someone tell me what is wrong with that data set there? Yes. Yep. There's one more. That's what Yeah, that's also a problem, right? That's not a number. Your machine learning model can't interpret that as a number. You need some way to make it a number. There's also one more, actually. Or if you can spot even more, that'd be great. But there's no year built for that one house there. But unfortunately, this is the reality of many data sets, right? Even though I said Kaggle tends to be very clean, at the end of the day, it is open source. So unfortunately, you may still come into situations like this. That is where you have to start doing the pre-processing work. So what about this data set? This data set is even worse, by the way. So this data set is supposed to be for movies, right? You can see here, the title year is like screwed up. You can see here, the country screwed up. There's somehow a null movie name. So yeah, these are just examples of noisy data sets that you will most likely run into in your project. Therefore, making it even more important that you look over your data instead of blindly shoving it into your model. Any questions? Okay, so by definition, Data pre-processing is turning raw data into clean, numerical, and consistent data that a model can learn from. So, like we said before, one of the most common issues is that some values might be missing. So you might be asking, well, how can we handle missing values? You have a couple of options. The first one is to completely ignore the data point. When do you think this is appropriate? Can someone answer me? Can someone give me a situation where if it's missing some category, you should just drop it as a whole? Sure. Yep. If it doesn't have an output or target, why use it? You won't even know what's going to be like what the final outcome is going to be. Or if it's like a very important category and it's missing, right? You can't use the information, right? Like for example, let's say you're trying to do a machine learning model for someone for some like biomedical application, right? If you don't have the patient's age, which is very important in your model, you shouldn't use that point, right? There's no point of using like a faulty data point like that. Now, there are some times where the category is not as important, and you can actually replace it with like the mean or median value of it. So does this make sense? Next one, categorical values. So we saw before that in your data sets, you might have words. So let's say I want to make a cat and dog classifier, right? And actually, let's say this is the data set you have. You have the weight in kilograms, you have the color as white and black, the class as dog and cat. But are we able to put these words into a machine learning model? Yes or no? No. So what do we actually have to do? Encode it, yes. We have to somehow convert this into some numerical representation so that your machine learning model is able to learn. Any ideas of what is the common practice for this? I know you probably know. But any ideas? Just throw them out there. Stab in the dark is fine. Yep. Yep, that could be an idea. That is very close to the actual common practice. Any more ideas of how you can encode that as a number? Yep.
0 and 1.
Yep, exactly. 0 and 1. More precisely, this is called one-hot encoding. So, I know that's also what you said. Both of you are right. So the most common approach is the following, right? Let's say I have a color category, and let's say I know that the color can either be red, yellow, or green. Well, what usually happens is you're gonna make that three categories and assign either a 0 or 1 to it. Does that make sense? Yep. So since there's numbers now, the model can interpret it, right? There's numbers, it's great, we can shove it into our model, and it can do its magic. So back to this cat and dog data set, what would actually happen here is the following, right? If you know that your dogs and cats can only be white and black, that's probably a pretty bad data set, but this is what you would do with one-hot encoding. Any questions regarding one-hot encoding and categorical data? Clear to everyone? Okay, last thing, scaling features. So this is a housing data set. Can someone tell me which numbers really catch your eye here? Yeah, yeah. If you look at the price compared to the rest of the data, it is huge. The problem is that in ML, these numbers are going to dominate, right? These numbers are so big that these small numbers are going to become negligible, right? They're going to have like no effect on the data set, which is horrible, right? Because things like the stories, the guest rooms, they're all very important to predicting a housing price, right? The same thing as the area, right? The area is still really, really big compared to the rest of the points. Any ideas of what you can do here? Yes. Yeah, normalized data sets. So there are many ways, like I said before, it's going to dominate. There are many ways to normalize it. The common practice could be min-max scaling. So min-max scaling, it clips all the values into between 0 and 1. You can do standard deviation normalization or z-score normalization. Let's say you apply the standard deviation normalization. The numbers become like this. Now, the numbers become a lot less interpretable by you, right? But for the machine, this is going to be much easier to process because these larger numbers are no longer going to dominate. Does this make sense to everyone? Right? So once you normalize things, it's very hard for this to become interpretable to you, but it's better to pass into the model than those raw numbers. Because the model will then know, hey, okay, well, I'll just convert that big number into this and then give the output. Does that make sense? There are many different normalization methods that you can research. These are just common approaches, especially if you're working with images, right? What values are RGB? What's the possible values of RGB? Does anyone know? Yeah, those numbers are huge. Usually what happens is you will do min-max scaling on those. So even a simple like data, right? Simple thing like a picture, you already have to do some kind of scaling. Any questions on scaling, by the way? Yeah, I forgot to type it in. I'm being completely honest with you. I just realized it now. Okay, last thing. So, who here actually knows about the training and test data split? A couple of you do. So, what actually happens is when you make a model, the proper word is you want the model to generalize. You want it to perform well on new and unseen data, right? If you just make a model that just memorizes your data set, what's it going to do in real life? It's like studying, right? It might not be the best example, but if you only try to memorize the lecture notes, and you don't do any tutorials, you don't do past exams, you might not do the best on the final exam, right? I'm sorry if I'm calling out anyone here. But when the model just memorizes the training set, this is called overfitting. You might have already heard of that word in other contexts. It is the exact same here. It is just memorizing the training set and being absolute garbage when it comes to real life applications. So to tackle this, for a beginner project, if it's a simpler machine learning model, usually you'll have a training set and a testing set. So the training set, like it says, is used for the actual training, right? So for example, if you have a data set of cats and dogs, you will maybe reserve 80% of the pictures to train the model on it. And then after you train the model on those 80% of the pictures, you want to see how good your model is doing, right? So you feed the remaining 20% of the pictures that the model has never seen before and see how it performs. These sets must be completely separate. So when your model is training, it should not ever touch the testing data set. Does that make sense? And does everyone understand why we have to do this? Yeah, because it's like pattern matching, right? You want it to learn patterns. You don't want it to memorize. So as a bonus, there is actually usually another set in between training and testing. Does anyone know what that one is? You do? Yeah. So if you are training a more complex model, a deep learning model that will take a lot longer to train. Let's say your model will take like 5 hours to train, right? Let's say you train it on all of your data and it comes out absolute garbage. You just wasted 5 hours of your life, but you're never able to see how well your model is doing during the training. So the workaround around this is something called a validation data set. So if you're doing anything deep learning related or like image recognition things related, most likely you'll need a validation data set. So what usually happens is, right, instead of 80 and 20, you usually split the data set into 70% training, 50% validation, 50% testing. So when you train, you're still going to train on the 70% of the training data, but while it's training, let's say after every iteration, you will put your model through the validation data set to see how well it's working. Does that make sense so far? It doesn't train on the validation set, it trains on the training set. But after a couple iterations, you see its performance in the validation set. If the performance is not improving, you can either just quit or you have to make adjustments to the model. Now, can anyone tell me why you should do this? I already kind of said it, but yeah. Yeah, but more generally, you don't want to waste time, right? Like I said, you could be training your model for 5 hours and then it comes out garbage. But a better scenario is, hey, I train my model for 15 minutes, and I put it through a validation set, and it comes out as absolute garbage. And you see no improvement on it even after 30 minutes. You'd be like, okay, this is bad. I'm gonna hit the reset button. I'm gonna go back, tune some hyperparameters, change some things in the model, and try again. Does that make sense? So after you're done training everything, yeah, yeah, but that'll just be your training loss. Ideally, you want to look at also your validation error, right? Because like I said, the validation is not used in training either. So in a sense, it's still looking at data that is never seen before, right? So for example, I trained my cat and dog classifiers for 5 iterations, right? And then I feed it the validation set, which it has never seen before, right? That's effectively seeing how well it is to work with unseen data. And then you use those statistics to tell you, hey, is my model going in the right direction? Is it actually training? Is it actually learning? Blah, blah, blah. So then when you're done training it and you're satisfied with your validation set results, and then you can use your testing data set at the end. Does this make sense? This should be very clear to everyone. Okay. Now I know the slide says that training and testing is enough, but if you really want the full like experience, you should really use a validation data set. So there you go. That is the start of your ML project workflow. It may seem easy. It honestly seems pretty easy, and it kind of is. It's really about what you do in these steps that really is most of your work, right? Like the work in your data collection, the work in your pre-processing. There's so many things to think of, even though these words sound very, very simple and general. So, anyone got any questions? Yeah, yeah. Like the first thing, you can either review, yeah, maybe watch recordings of phase one or phase one slides. You also have a lot of online resources that are really going to be helpful. And hate to say it, GPT can help you a lot as well. Well, at this point, it depends on what you want to do with your project, right? Like phase one had 7 weeks, I think, had 8 weeks of content, right? There's no really need to look at like the slides where it's not relevant for your projects, right? Like let's say I want to do like image classification, right? I don't think I'll have to look at linear regression for that. You most likely will have to look at like the neural network section of it. Okay, any more questions? Yeah, I agree. I heard that. Okay, so after all of that like planning and stuff, you might be asking, well, what model should I use then?
Okay, good transition. So, okay, in terms of choosing your model, the first thing is about the like general architecture and style that you want to do. So the best thing you could do is probably to leverage the strengths of each particular model, right? So the first thing you have to do is think about what's the nature of your data, right? It could be like images, or it could be like table, or it could be like text or time series data. So there are different natures of data. Um, and you're supposed to start with like what's commonly used by people like in general, right? So for example, about kind of image data, it makes more sense to use like a convolutional neural network, which is designed to deal with images, right? And if you have text data or time series data, it makes more sense that if you use like RNN or something like that. It wouldn't make too much sense that if you use convolutional neural network for like text data or time series data, right? I mean, it could work, but it's not like the best because you're not really leveraging the strengths of the model. While there are more like nuances into it, or you can use more general based model like transformer could pretty much work with everything, but for some instance you do need some modifications to it. So, but yeah, but the first step is just to think about what kind of data you have and then what kind of model will best deal with those kind of data. That makes sense. Um, and second, so you probably will ask, oh, right. There are different like sizes of model. There could be like you could have a model with 10 parameters, or you could have like 1 million, or now like language model would be like 70 billion parameters, right? So it's like, oh, how do I choose my model size? So there are multiple key factors here. So the first one is the amount of data you have. And as Warwick said, the amount of data you have is crucial. It depends, I mean, on multiple things. So first of all, you probably remember from his presentation that there are overfitting and underfitting in like training, which you probably see like all the times, right? So overfitting means that you do not have enough data, but you have like a relatively large model or complex function. So it basically remembers everything, right? So it's like on the picture on the right, you basically draws a very complex boundary that doesn't really represent your data. Actually, it's just fitted for this training data, right? And you could also have like underfitting, which is not shown by image, but it's like your model is like you have too much data, so it means your distribution or data is too complex that you cannot just simply draw a line like to separate them, right? But your model might be just a line, so the best it can do is draw a line somewhere, and then it performs pretty bad. Uh, so yeah, so think about the amount of data you have. If you have lots of data, it's probably better to use a larger model, right? And then if you have like a smaller amount of data, it's probably to start with a small amount of no, a smaller model. And second is the amount of compute you have, which we'll talk about a little bit later. But just the idea here is that if you don't have like enough compute, you can't really train a big model. Like there's no way you can train ChatGPT from scratch, right? Because it needs like probably take you a billion years on your computer. But yeah, so think about like how much resources you have is also crucial. And also in practice, you should think about the downstream cost, right? So let's say I train this model. Um, let's say I train a chat GPT or somehow I did it, right? But I deploy it and then I'm gonna like let a billion people use it. Then there will be like your basically your model is working like all the time, right? So you have to think about the cost of that and like how do you like set up your infrastructure, whatever, to support this um, like billion user capacity, but that's not your concern right here. But in practice, that's something you should also think about that, which is arguably more important at inference time. Yeah. So the first thing, like when we talk about machine learning, is like that comes to your mind would probably be that you will train your own model, right? So, and it's just basically meaning learning whatever data you have from scratch, right? And it sounds really cool. It's like, oh, I trained my first machine learning model too, and you say it to people, people think you're very good. Um, but generally, training your own model from scratch is probably not the best idea in practice. And you should only train it if first you have good amount of data that your model can work with. And second, you have lots of compute because training does takes quite a bit of time and also compute, right? And then there's also no good prior model exists. So basically meaning that no other model um, that existed could like deal with your data somehow, which is generally not the case, right? And the fourth thing is that when you're implementing a new architecture, of course, you have to train everything from scratch to like see the performance, whatever, because there's no pre-existing model that built for you. So you probably have to start from scratch. But well, if you want to implement your own architecture for sure. But uh, yeah. So there are also something called transfer learning, which I don't think we talk about in phase one. But the basic idea here is that you take someone else's model that's being pre-trained. That's what we call it. So you take a pre-trained model, which is trained on some other data, like with similar data by other people, and you use that to, or you train your own model based on that model. So as an example, let's say someone trains a cat and dog classifier, right? And then it performs like pretty well, let's say. Now I want to do, I don't know, like tiger classifier, which the model doesn't know, but it already learns about what a cat looks like and then what a dog looks like, right? So you can say that tiger is arguably somewhat similar to a cat. And so basically what you do is you can take that uh, pre-trained model and you can further train it on your own data set, which is the tiger data set, right? So you don't have to learn like your model doesn't have to learn like what's an ear, what's a mouth, what's an eyes from scratch. And they can just learn, oh, like tiger is like a little different from cat, but it doesn't have to take as long to train, or it doesn't need as much data to train as well. So transfer learning is especially good if you have a smaller amount of data and you don't have too much compute and there's some like pre-existing knowledge that you can leverage. Yeah. Do you have any questions about this? No? Okay. And as a rule of thumb, transfer learning will and most of the time gives you better results than train your own model. Um, yeah, but honestly, for the purpose of this, like projects, I don't think it matters too much if you train from scratch or do transfer learning. Although compute and data is a bottleneck that you have to think about, but like the learning experience should be the same. Like whether you're doing training your own model or doing transfer learning, the workflow is pretty much the same. So it doesn't like really impact your learning in this case. But in practice, transfer learning is always like almost always a better choice to start with. And also evaluation, right? So you might say, oh, I train a model. How do I know it's good or bad, right? Um, so first thing, as we talk about in, we talk more about this in like phase 1, week 7. So if you want to learn more about evaluation, you can watch the recording of that or read the slides. But the idea here is that you should always start with a very simple model, right? Let's say I just train a linear classifier on whatever data I have and then see how well it does. And then the goal of machine learning is, or like the project is to see how like whatever you can do to make the um, performance of the model to be better, right? So maybe I train like a simple linear classifier on my data and then achieve like 60% accuracy, which is, let's say, okay. And maybe after you do something like changing model architectures, right, or whatever, you reach 90% accuracy. So that's something you should report for, which is like the work you've done to improve the performance of. Okay, anyways. Yeah, so something you can do to like on your base model is like you can do feature engineering, right? Like um, I mean, like you can crop your images or rotate it or like apply different lighting, for example. Or you can try different model architecture, right? So let's say I start with a simple linear classifier. And then what if I switch to a convolutional neural network? It will probably perform better on the image data set, right? And you can also try something like different learning rate or longer or shorter training loop, right? That could probably prevent you from like overfitting or underfitting. And there are also different optimizer that you can use to see the performance. Typically, different optimizer will give you somewhat different results. And of course, there are more, like a lot more different things you could try. And yeah, but in general, there's lots of things to try, but you should always start with a base model. And you should, yeah, try different alternatives that to see which one does the best. And in general, there's no like a single way that I can say you just do this and you get a best performance. Um, Usually you just have to like experiment and see whatever like things gives you the best results. And in terms of evaluation, you should do evaluation in like multiple ways. So, which is like F1 score, for example, where you see correlation, loss, right? So those are things, some of the things we talk about a little bit about in week 7. So you can do reviews on that. And yeah, you can compare those evaluation methods across different setups. So you will see that how basically the evaluation metrics will kind of tell us how good your model is in this particular task, right? And there are also some specific evaluation metric that you have for your particular problem. For example, for language task, you've probably heard of a blue score or something. That's uh, so those more specific metric you probably have to search up yourself and then see how to implement those. But it shouldn't be too hard in general. And I think one common misconception is that you like please do not just look at loss and accuracy, because it's somewhat biased estimator. You should look at more metrics that gives you like full rounded information. Um, because the reason is that higher loss and accuracy doesn't mean it's the best performance in most of like it doesn't like guarantees it gives you the best performance. You should look like precision recall, all those different things that gives you different indicator on different kinds of scenarios. But that's also pretty problem specific, so you have to do some research on your own. Yeah, so now let's talk a little bit about compute. So you probably wonder like if I'm going to train my own model, where I get my compute from. So we provided some options. So the first one is like Google Colab. Hopefully lots of you have heard of it or already used it. So there's like a free version, but you probably can't really access their GPU if you're using the free version. The paid version is like $13 to $15 a month. Um, yeah, and it allows you to access Google's GPU, and it's pretty fast. So it's not really the fastest, but it's good enough for this purpose, I think. Um, but there is like a issue that Google Colab is kind of hard to collaborate on. So if you have ever used it, it's not that good for collaboration. But still, I think this is your best bet if you need reasonable amount of compute. And as we mentioned, the second option is transfer learning. So you probably have take someone else's model that will significantly reduce the amount of training time you need for the compute you need. Um, but that's like also very problem dependent. And technically for transfer learning, you still need training, right? So it's probably not a good idea to use like a CPU for it, just on your local computer. Or you have local GPU, but that's like only you have access to it, right? Like if you're a gamer, you probably have access to some GPU. If not, you probably don't. So yeah, and it just takes some extra work to set things up locally, and they can be like a bit complicated. But overall, this is like the free thing that you can take. So yeah, overall, I think Google Colab is still your best bet because it has like lots of packages and whatever things take care of you. So you can just hop on and use it directly. It's the easiest to work with anyways. And another thing is that before you choose any like of the options, or there might be more options that you can have, but the first thing you should think about is like you have to do a estimation about the amount of compute you need, right? So, and then you'll see, oh, maybe I need a bit more compute, then I'll have to buy maybe a Google Colab. And then you see, oh, if I can use my CPU for training, that's good enough, then you probably don't need to spend money on things. Yeah. So, any questions for this section? No? Okay. I mean, like these part are very overall very problem specific. So these are just like a guideline, but when you formulate a project, you probably have to think about those things a little bit more on yourself. And then you can also like we kind of think we'll ask you to specify those in the proposal, and then we'll see if that's like a reasonable like model or compute that you'll think about. So yeah, but we'll give you some feedback for your proposal on those things if you decide to include them. Yeah. Okay.
Hello, hello. I guess like before I start this project walkthrough, I'm not sure if you guys mentioned RL projects.
No.
Okay. But yeah, I guess I just do want to like give like an honorable mention to RL projects, especially since like I also really enjoy RL. But if you want to do that, basically, let me just try to escape this. But I guess like the process of that would be a bit different, since like RL trains from trial and error, and most likely you're going to be dealing with like online RL, which means like your agent will be like actively exploring the environment. Um, what happens here, like in that project workflow, would be more like you would have to like kind of build your own environment first, and then you would be applying them, and then you can sort of run inference. So I guess like if any of you guys participated in AI squared, then you might be sort of familiar with that process. But yeah, like you can ask me about any like RL if you're interested in that type of project later. I'll be happy to answer any questions after the session. Okay, so project workflow. We're gonna have some fun. Let me access my GitHub because I think I'm just gonna be presenting this on my GitHub, just the code. Everything is quite um conveniently placed inside a notebook, so it's actually perfect for explaining this today. Oh yeah, okay. Let me just talk about the project in general. So, you know how we first said like we'll start with the problem definition for our project. So, if you guys like anime, I mean I like anime. Um, he likes anime. He likes anime. Yeah, yeah, mashallah. But basically, yeah, so this is my first ever ML project. I built this after taking like sort of like an MLF by Andrew Ng, who's like ML researcher, Stanford. He has a really cool ML specialization, but of course MLF is better. Um, but yeah, basically one of the things that he talked about was content-based recommendation. And basically what that is like we basically have user ratings of animes and also like kind of like the genre scores of like animes. And then we try to just compare the two to give a final prediction to basically see how similar um like the anime is to like what the user likes. So that was the first project that I did, and I'll just be taking you through sort of like how it aligns with the project workflow that Ward presented today. And yeah, so let me just make sure that I have the workflow out. So, um, so yeah, I guess like first, so yeah, that's the problem definition. It's also going to be regression, as well. It's not going to be like classification, just because we're trying to predict like similarity scores. So data collection. So basically what I did for this project, there was this anime data set on Kaggle. I don't think I'm gonna try to find it. Um, but that's how I got my data. I just downloaded the data set from Kaggle and then just loaded it into my computer and then just trained everything locally. So data inspection, exploration, and pre-processing. Okay, this is where I'll open up the notebook. Yeah, so basically, for all the data pre-processing, if you're going to be working with Python, most likely you will. You'll be using this package called Pandas. So it's very good for just anything data related because you can put everything in like a convenient data frame and just load it in, right? So uh, basically here we have like a bunch of data with anime, so like uh Cowboy Bebop, Trigun, everything here, and then we have a bunch of what's it called, features, like raw features from our data set. So we have a score, genres, number of episodes, all of that. uh so yeah, that's basically what we have here, but as you can see, right, some of these features are kind of useless, right? Like at least like when you guys may be looking for something to watch, like do you really care about the studios or the, like the producer? Probably not. Maybe, probably not. I don't. So that would be like the type of things that we would have to clean, right, in our data. Um, so yeah, I guess like I'll just try to make this sort of quick so I'm not like yapping too much. Um, and I'll just quickly talk about how I sort of process this data to make it good to go for our model. So here I dropped all of the features that I don't really need. And then this is what I was really left with. Like the anime ID is just there for reference later. And then we just have to name the anime so that like when we actually run inference on it, like we can, get that output. And all I really needed was the score, the genres, and how many it's scored by. So I'm gonna skip over this. You can explore my yeah. I'm not going to talk about that because there's a little sus things there. Um, but yeah, like also here, basically for NaN values. So I could have probably handled this a bit better, but I just literally just dropped any anime that didn't have any or didn't have like valid values. So that did kind of like significantly decrease the amount of data I had for training, but it's okay. It still worked out at the end. So, um, yeah, okay. So basically, I did the same process for both um, the the actual items, so the animes, and for the users, right? Because remember, we have like two separate data sets that we want to like compare together. And yeah, so I guess like here is when I'll talk more about like feature engineering. So I guess if you guys remember what feature engineering is, it's basically how can we transform just raw data into features that are like actually important and we can actually use for the model to kind of improve quality. So here, what I did is I applied a Bayesian average. So basically, what that means is like, you know how with sort of ratings and stuff, right? Uh, like when you rate something, it's like, I guess the rating of something, sorry, is like less trustworthy if there's like less people who've rated it. So basically, Bayesian rating, what it does is it just basically scales down those ratings if there's less ratings on it currently. So that's what I first did for the feature engineering. I'm not going to go too much in detail in like how like the formulas and stuff, but again, if you're like curious, this project's on my GitHub, and it's in this framework folder here called framework.py. And yeah, so you can see that I basically scaled it down, like the scores here. And then I also have weighted genre scores for each user. So basically, what that's doing is like basically, you know, how users could have rated like multiple animes, right? So basically, we want to kind of like compress that down into like just one user and just sort of like all of the genres that they just generally like. So just like summarizing that for each user. Um, and then yeah, we basically do all of these changes to each of the users and the items. And yeah, this is literally all I really do for the data processing. Scaling the shapes. Yeah. Okay. And then we do normalization as well. So basically that's just to scale everything into sort of like a range, right? Just so that we don't have too big ranges that cause overfitting, I believe. Yeah. Um, and that's what I do. I have like a z-score normalization function also somewhere in framework. Um, and these are just like helper files and helper functions that I'm calling to do this. Min max scaler as well. It's also just to scale down the Y train. So basically, this is scaling down like the X and the features that we have, and this is for the Y train. Uh, and then yeah, this puts it into NumPy arrays to basically put it in like a format that we can put into the model for training. And by the way, if you're curious about anything, like I'm kind of like going this really fast and like kind of unorganized, but you can also just stop me if you want. But yeah, this is like all I'm doing here. I'm basically making like the sizes as well, um, constant. So like because we want to have like the same shapes, right, for training between both the items and the users. So I'm also changing that to updating this as well. And yeah, this is into like the model now. So, uh, you know, how work discussed, splitting into train and test sets. So that's what I also did here. So I split into 80-10-10, for training, for testing, and for validation, called it cross validation here. But yeah, you can see how like the shapes here are kind of updated, as well, and it's split right here. So now we go into choosing, you know, models, right? So I guess like choosing the model for this project for me was like very, very quick because it was inspired by something that I already learned, and then I just wanted to like sort of apply that for my own use case. Uh, but yeah, I basically did this double neural network architecture, right? So we can train the model on both user content and then movie content. And once it learns better features at the end, we can just dot product them to give that predicted rating. Also, I guess just to mention here, I was really interested in exploring the theory myself and like how deep learning works. So I created a neural network framework from scratch. Now I guess like you guys like definitely don't need to do that. You can just use PyTorch, and honestly, that's fun as well because in industry and research or whatever you do, you're never really going to make a framework from scratch anyway. But if you guys are sort of interested in learning and just sort of what's it called, solidifying your knowledge of deep learning, then I guess you could also do that as well. Um, and yeah, basically all of these things that I basically just made from scratch. So atom optimization, won't get into that, but you can also uh, kind of refresh that with the phase one material as well. Um, and then I also did L2 normalization as well. So, but yeah, basically this function is just like just our model optimization. So just basically looping through epochs, mini batches, and then we're just training all of these together, right? Uh, and I also did something called early stopping. So I forget if we've ever covered this before, but early stopping is like basically when you see that your validation loss is like starting to go high, then we can stop the trading there. Um, so yeah, I this is also just my chosen network architecture. So uh also like with this, I would just say play around with the architecture too. I mean if you have the resources, just so that you can see maybe what architecture works best, right? Um, because it's really hard to just find an architecture, I think, because um, like there really isn't sort of a lot of well, I mean, there's research into it, but it's still being explored. It's like, what's actually going on in these neural networks, and yeah, how can we choose a really good architecture? Like that's something that I think can be played around with your experiments when you do tackle your own projects. But yeah, you can see that the loss did go down, and then I mean, like the graph kind of extended like a lot, but you can see that it went down, and then we were able to stop it uh, there. So didn't take too much training, um, but yeah, it did work out, and so um, but yeah, like all of this is really just at this point just storing the models in an inference. So here I use Pickle to just store the model parameters, like if I want to use it later. Um, and then yeah, I mean like there really isn't like an accuracy metric I would say, but uh basically my accuracy was like comparing two values, like the predictions and then like the test. Uh and basically we can see like there's some predictions that were sort of close like this one, these two. Some that also weren't, but yeah, we have like a kind of like a messy correlation. So it wouldn't be the most accurate model in the world, but still did work. Uh, but yeah, and then once you have the trained model, right, we could just load it in and have predictions. So basically, what the prediction would entail, right, is that we would just have like the same features of the user vector, and then I just basically just add the values there, right, and then I can just run the model. So I just construct the vector, um, and then yeah, I'm able to load in the model around here, and then I'm just able to where is it? But I just load in the model, put the user vector into the model, and then all of this is basically just running the model here and just putting this into the table and then solidifying it into like just the top 10 predictions. So that's basically the project right there. That's like kind of like the overview of what I did. And I guess like just to say like once you've also finished um, your inference, what you can do is also build something. So like I suck at full stack and like anything front end, but I wanted to make like a GUI for this model as well, just to just finish off the project rather than just like having like a raw model. Um, so that's what I did here as well. I mean, you can just see the demo. I'm putting in the values for award winning and romance. and then I'm getting my neighbor Totoro. Goat animes, award-winning goat animes. But yeah, that's basically what I did. So this is my first ML project. I Yeah, that was a very questionable presentation. But I hope that it did like have some sort of inspiration on you guys. Yes. Oh yeah, GUI I just built with this thing called custom C Tinker. I forgot what it's called. But it's just like a Python GUI, and then you can just see like the views. I just have a bunch of pages, right, for like a home page, the prompting page, and then just like the recommendation page when I just put all of the animes, and then like this is really just a lot of just front end development at this point on Python GUI. Probably want to make like a website though with like JS, HTML, CSS if you want to do some front end. Python GUI is not really, I think, used or important. So yeah. Okay, are we done?
Um,
Kind of. Okay, perfect.
So yeah, thank you, Kaden, for the presentation. It's very good, right? So yeah, I think that's pretty much for us, right? So for the remaining of the time, I'll just give it back to you guys so you guys can think about ideas, think about group, because in the end, we do expect the project to be done in group. When you submit your proposal, it should be done as a group. So yeah, and then we'll stay here for a while to answer your questions, or if you want to discuss your idea, you can come up to us, and then yeah. But otherwise, that's pretty much that. And hopefully see you next week for the proposal workshop.